Professor George Summer served as the scientific leader in data center at RISE Research Institute of Sweden, where he leads pioneer research on sustainable and energy efficiency on data center. He also holds the academic position as an adjunct professor in fluid dynamics at Luleå University of Technology in Sweden, and as a visiting professor in thermofluidodynamics of the University of Leeds in UK. And Professor Summer, with over 25 years of experience, has led a lot of government industrial funded projects focused on high-performance computing, thermal management, and energy optimization within data center. His work has been instrumental in advancing liquid cooling technologies and integrating waste heat recovery system, contributing significantly to reduce the environmental impact of the data center. Beyond his research, Professor Summer chairs the Future Technology Symposium under the Open Compute Project Foundation, guiding global discussion on the future of sustainable computing infrastructure. Please join me in welcome Professor Joe Summers. Now it's ready, and the floor is yours.
Okay, thanks very much. Yeah. So yeah, I work in the north of Sweden. There's a slide here which show you where I actually work. I work for Research Institutes of Sweden. I've been there 8 years. It's a research facility that is dedicated, is part of RISE. So RISE is a very large organization in Sweden, a lot of different units. And it's focused on the data center systems team with the ICE data center facility is focused on data center infrastructure. So we're looking at making data centers more sustainable. So you can see some of the test beds that we have here in the north of Sweden. So we've been looking at, we run 2 production data centers, small production data centers, which we use with a lot of our collaborators. And we run a lot of different applications on there, Hadoop, Open Nebulas, Open Compute cluster as well, and a lot of other infrastructure. And we focused a lot on, with our partners, we have founding partners, which are obviously from Sweden, Ericsson, ABB, Vattenfall, and of course there's a very large data center next door to us in Luleå, which was the first open compute data center in Europe, which is the Facebook, or it's the Meta data center. There is one sign, it's the only sign I've ever seen, which says Facebook data center with an arrow pointing to the gate. I haven't seen that anywhere else in the globe. We've won a lot of different awards for some of the research that we've been working on. And it's really strengthening the AI and data center ecosystem to attract researchers. We do a lot of Erasmus exchange as well. So if anybody's interested in sending students to work with us, we're always open to that as well. What am I going to talk about today? I was thinking about a number of different things because I've worked on lots of different projects. I would probably like to focus a little bit more on what's driving the energy consumption, and that's the growth in AI and the infrastructure around AI. So you build a data center not because you want to manage heat or power. You build a data center because you want to supply digital services, and those digital services run off IT. And it's looking at the trends in IT that I wanted to do. So I'm going to look at the growth in data centers, looking at the energy and compute needs for digital requirements of AI, and then do a deep dive in the compute energy and the efficiency going forward. I'm going to talk a little bit about the managing of the heat, which is, so some people like to talk about heat, others talk about cooling, but it's the same thing. It's getting the heat, the energy that is absorbed by the IT systems is converted into heat, and then that has to be managed. And then there's a lot about monitoring the sustainability. So I will say a little bit about that at the end. So I asked a very famous AI tool, how much computing power will be needed in the future by 2030. And it came up with a diagram like this, which was a hyperscale data center with zetaflops all over the place. I hope you're good at your prefixes because I'm going to use a lot of different prefixes in this talk. from atto to yotta. So if you know what an atto is and what a yotta is, then you'll be fine. I'll remind you when we get there. But the interesting thing about this is there has been some research done on this. A very famous paper by Hilbert and Lopez, the world's technological capacity to store, communicate, and compute information. And in this paper, they talk about all those aspects. But the other interesting thing about it is that probably because they're the only ones, the only source of information out there at the moment, is it has been referenced, cited quite a few times, over 3,000 times, this paper. And it was cited by a very famous piece, or a very good piece of work, in my opinion, which is actually the Semiconductor Research Corporation's decadal plan. And in this decadal plan, they were looking at the compute energy in joules per year going forward. So on the diagram in the left there, you've got those orange dots are indicating the transistor energy dissipation, which I will come back to later. We've managed to reduce the dissipation per transistor over the years, and that's linked to a law called Moore's law, in a sense. But one of the things going further from 2030 onwards, our ability to be able to do the compute on the right here, which is measured in zeta instructions per second, is limited by our ability to generate electricity. Okay, so the dynamic, what they're talking about here, the market dynamic limited scenario in this report is because we need more and more energy. And I think even if you look at some of the talks by some of the aficionados in the AI space, Sam Altman, I think, said we need better ways to generate more energy, or we need to find ways to generate more energy. We definitely need more energy to do this. Maybe we don't need to do it, but at the moment, and this actual report was written before the Gen AI explosion of from November 2022. This was written in 2021. So focusing on that, what is a data center, first of all? And I thought, well, I'm not sure if most of you have seen anything. There are lots of pictures in the media about data centers, and it's quite a hot topic in Ireland as well. I know that for a big fact. This is actually the data center that's co-located right next door to our facility. It's actually Meta's data center, Facebook. You can see does this have a laser? Yeah, you can see this is the first one that they built. This is the second one that they built, and this is the third one that they built. And this is inside the first one. And there are 4 halls, and each hall is around about 3 football pitches in size. And it's got a considerable amount of compute. It pulls a lot of energy off the grid. Thankfully, in the north of Sweden, it's easy to get rid of the heat because there's only 5 or 6 days of the year which is over 20 degrees centigrade. The energy comes from hydroelectric, so it's renewable sources of energy, and there's a good fiber connection to Stockholm, so there's good connectivity. So they've got everything they need. But the interesting thing is, nobody really knows how much energy they're pulling off the grid. I mean, when it was originally designed, it was supposed to be a 90 megawatt data center, but it's probably pulling around about 150 megawatts today off the Swedish grid. Our facility is actually located just here, and this is the Facebook facility here. There are lots of reports about energy demand from data centers, and of course this has been revised as the AI revolution takes hold. This was actually from the International Energy Agency's report on electricity in 2024, and it was forecasting to 2026. And of course, whatever trajectory we take, whether we get to one petawatt hour of electricity demand for data centers by 2026, we're around about 450 now. There are debates around that because do you include crypto in that calculation or not, and other types of data centers. But the thing is whatever trajectory we take, there is a lot of involvement of different stakeholders now. Governments are involved because it's pulling a lot of power off the electrical grids. Green lobbyists are involved. Communities are also involved because you're in, particularly if data centers can be a force for good in one sense, if they can help the electrical grid, balancing the grid, because we do have a problem with balancing our electrical grid with a lot of renewables in the grid, then data centers can help there. So they can be community players. Also, reusing the heat is another thing that we're considering as well, and we're trying to see what are the best ways to do that. And obviously there's a lot of media attention, and the media doesn't always say the right thing, but does it ever? So when you look at the European data center market, this was an interesting analysis from the same report. Obviously, post-COVID, we were on a downward trajectory in our electricity demand. And then all of a sudden, we're in this demand recovery period now, 2024 to 2026. And this actual report, again, identified 3 areas of major growth. Electrification of mobility, electric vehicles, electrification of heat pumps, and data centers. So there's a lot of different, so the growth in demand for electrification, if you like, of everything is around mobility, heat, and digitalization is what they're saying. And obviously the digitalization is also another way. I mean, this conference is ICT for sustainability. We talk about the sustainability of ICT, but there's also ICT can provide sustainable ways of doing things. And that's what's been talked about sometimes about the data center. So inside a data center, and this is actually some research that was done from the Lawrence Berkeley Laboratories. They have a data center research group that's looking at this. It's quite complicated. But the legacy data center of old, 38% of your electricity went into the IT equipment. That's the thing that generates the money. So, you've still got 62% of your energy is going somewhere else, just managing that IT. That was not the right way to do things. We have a lot of cooling infrastructure and obviously power distribution. So power distribution is minimal, but most of the energy is going into cooling the data center. Now, going forward, the more modern data center, you're now looking at 70% of the electricity is going to the IT. In fact, the hyperscalers are at 90%, 85 to 90% of the electricity is going to the electricity. They're putting a lot less energy in the infrastructure around. And so, but when you actually look at it, the heat transfer train is from the microprocessor. This is the thing that is converting the electricity into heat, electrical energy into heat. And then we have a number of heat transfer processes where we reject it outside, or we try and make use of that energy from the ICT equipment. So I'm going to try and look at the aspects of measuring compute efficiency, and I'm going to do that using floating point operations. Now, floating point operations, it does depend on the size of the floating point number. And this is what I'm going to show you in a minute, that there's some interesting points here about what we're building in terms of AI and the traditional HPC system. So one way to look at this is that, in a data center, you have so many racks. You saw that picture with racks. And in a rack, you've got so many servers and you have so many sockets, CPU or GPU sockets in a server. And then they have so many cores per socket. And then it's the flop per joule, the amount of compute you can do for a joule of energy is one way to look at it. But that gives you the total amount of energy you're going to use to do the compute. The other way to look at it is obviously the rate at which is compute. So I've capitalized this S and made it red because this is floating point operations per second, which is different from the one at the top, which is total floating point operations. And again, that depends on the cycles per second, the actual clock rate of the microprocessor. And there's another way of looking at it, which is in instructions per second. But in terms of, if we're looking at flops here, one of the things that we can do is we can look at unoptimized GPT-4. And this is and although they don't although OpenAI are not very forthcoming with all the information, there is a little bit of information that allows you to do this kind of calculation. So there is approximately 1.8 trillion model parameters in that trained model. 13 trillion tokens were used, and you use 6 floating point operations per token. Now, it's quite straightforward then to multiply all those 3 numbers together and to get the total amount of compute you need to train GPT-4 unoptimized. I say unoptimized because things have moved on since then. So it's an old slide, really. But it's 140 yottaflops unoptimized. So then you say, well, let's go to our HPC systems in Europe. Kayani has Lumi is the largest, is the one highest up on the top 500 in supercomputers in Europe, and that's in Kayani. It pulls 9.5 megawatts when it's at peak. All of that energy is transferred into heat for the city. So they use heat pumps and they reject the heat to the city. So they're good community players for the city. But if you do the division of the peak performance of that, which was 530 petaflops, now notice this is a red S, this is per second. If I divide those 2 numbers, it will tell me how long it would take to train GPT-4 unoptimized on Lumi. And it will take 264 million seconds, or 8.4 years. So you wouldn't use HPC Lumi to train GPT-4. That was, and if you do the calculation on the energy consumption, you're talking about 700 gigawatt hours of electricity, and that's about 70 million euros. But we do know from OpenAI that they trained it on GPUs or NVIDIA A100s at the time. And the interesting thing here is that they 620 teraflops per GPU is the throughput, and that's at FP, that's at 16 floating point arithmetic. And that's the difference, because Kayani here is at 64-bit. And their training time, and if you work out with the 25,000 NVIDIA GPUs that they had, it works out about 101 days, the training. So they managed to train that, and they said the cost was $100 million and 54 gigawatt hours of electricity was consumed. Of course, that's just training the model. That's not us actually using the model. And so to use the model, we go into what's called inference. Now, inference is a bit more difficult to calculate because you need to make quite a lot of assumptions. Again, going back to the GPT-4 model, 1.8 trillion model parameters with a maximum of 32 kilotokens per available, with 2 floating point operations per parameter for 1 token. And say we assume, say that 1 request is 1,000 tokens, then you can do the calculation. It needs 3.6 petaflops per request, which equates to about 1.5 watt hours of electricity. And there's some other numbers here. 1 watt hour is a 60-watt light bulb on for 1 minute. But even if we did have a cluster of 128 NVIDIA A100s for inferencing, if we had 100 million active users with 2 requests per day, you're looking at quite a lot of computing per day that's required. And again, that's around about 91 gigawatt hours per year. Now, that slide was written about 2 years ago when we did these calculations. And since then, I have seen a paper, which is interesting. Remember the 1.5 watt hours there? In this paper, one thing to note is that suddenly we now are doing deep research as well. You can switch on reasoning, and that uses 20 times more energy than standard requests with ChatGPT, for example. This paper here, what was interesting is that here, 1,000 tokens, which is what I had in the calculation, output size 1,000 tokens. They've got 4 different models here. You can see it running on different infrastructure. So GPT-4o and then GPT-4o mini running on NVIDIA's H100 or the A100. But the interesting thing is 1,000 tokens is around about 1.5 watt hours, which is what I calculated 2 years ago. And that paper has just come out. It's a preprint in 2025. And it depends on what infrastructure the throughput. Another way to see it is the tokens per second. And it depends where you're running. If you're running on OpenAI's data center or you're running on Microsoft Azure, which is a cloud platform, you can see the throughput, the wide range of throughput with these box plots in terms of the tokens per second. But obviously, the more tokens you put into your request, the more energy you're going to consume. And if you've ever used the free aspect, when you start using one of these AI tools freely, you are limited because suddenly it says, sorry, you can't use it anymore until another 12 hours or something, because they're limiting the energy use. So we talked about this, these A100s. What does the data center look like made of A100s? And I thought it might be interesting to see this infrastructure. This is the box here, which is a DGX A100. It's got 8 A100 GPUs in it. And you can see it's got 8 massive fans at the back here. And then that's at the front, actually. And then at the back, you've got 6 power supplies. And in a standard data center, because you've only got usually 2 tap-off points, the connections for electricity, you've got a tap-off on 2 feeds. So the way that we operate data centers is that we operate them with 2 feeds, 2 electrical feeds. So all of our IT has an A and a B feed. And the reason we do that is that if the grid goes down, then we can fail over to generator using one of the other routes. And based on the fact that we can only get 2 63 amp tap-off connections, an A and B feed, we can only get 4 of these in one rack. Okay, so that's a standard rack of around about 2.5 meters high. And so in order to the 25,000 A100s that OpenAI were talking about in 2023, when they were doing the training, would have had 780 of these racks. And each rack is rated at 20 petaflops of compute performance, and that's per second. The interesting thing is that if we compare the 64-bit performance of those 780 racks, which actually consume 22.3 megawatts of power, and you compare that with Lumi, it's actually only 242 petaflops as opposed to 530 petaflops for Lumi, if you wanted to use it with 64-bit arithmetic. But of course, AI, so we're building infrastructure that if we were going to use it for high performance computing, the real hardcore high performance computing, which is used for, say, climate modeling or the collision of galaxies, which you need high performance, you need accurate compute, then this 780 racks would not be so good as the 80 racks that Lumi has. Something to think about when we're building these data center infrastructure. We're building them, these are what is called approximate compute. It's not so accurate compute as the original HPC that we are running today. So what's going on inside a data center then? So there is a piece of research, and I am a great fan of a lot of the great scholars of the past. Whether it's Richard Feynman. Richard Feynman spent 10 years of his life working on computing, the last 10 years of his life, and he could never understand why we built systems so energy inefficient. He said engineers should be ashamed of themselves. But Rolf Launder was an IBM researcher back in the 50s and 60s. He wrote a very famous paper here, and it's called Irreversibility, and that's the key, Irreversibility and Heat Generation in the Computing Process. And if you look at his work, you will see that if you work out the amount of energy you really need in order to produce the ones and the zeros, the digital information, the amount of energy in that information coming out as a fraction of the electricity going in today is 0.03%. So 99.97% of the energy going into the IT infrastructure is wasted, in a sense. It's not going for the core act to change it into ones and zeros. So that's a measure of the efficiency. Well, going back to the 1970s, it was even worse because we built the infrastructure better, but we're still struggling to make this efficient. And then I like to relate that to something that got banned. The incandescent light bulb here, 100% electricity in, 95% heat, only 5% of the energy went into light. But we all know what happened to that. It got banned. So on the same basis, we should be banning data centers because they're so energy inefficient. But that's something to think about. Anyway, so the argument is that this heat that comes out, which is not even a grade of heat, it's not a high enough temperature to do anything useful with, is the struggle. We have to upgrade that heat, and there are lots of ways of doing that, and there's lots of research on that area, which I won't touch upon today, I'm sorry, but that is something that is a big topic that I'm working on as well. But I wanted to focus in onto why they are, what is going on, and where is the efficiency of the compute going. And this is the energy efficiency of compute is interesting. So if you look at this diagram here, which is a very interesting diagram going back to the 1940s, the transistors in the 1940s were, you needed 0.001 joule of energy to switch a transistor in the 1940s. By the time we got to sort of the late mid-90s, where we've rapidly reduced the voltage. As we drop the voltage, as we lower the voltage, the energy dissipation is related to the voltage, and I'll come on to that in a minute. But we've also reduced the clock frequency as well. We've stagnated the clock frequency. We're not increasing the clock frequency. As you may have remembered, some of you old enough remember going out and buying a computer because it had a higher clock frequency than the one you had before. The clock frequency is no longer a topic, but you can see where we're going. There's a different international technology roadmap for semiconductors. Lambda limit. This is the theoretical limit. This is where we should be, because that's where all the energy goes into just producing the ones and zeros, and not wasted away. But we've got a long way to go. This is a log plot, don't forget. So we've still got a long way to go. When you get to 2030, we're only going to get to 1 attojoule per transistor. And then when you put it into, say, floating point numbers, you've got all this different here. So if you've got FP64 here, you can see that it's been decreasing over the years. So we are making it more efficient. But it's we're still a lot of headroom we have in the compute. And really, if you want to know why that is, it's because the compute process is irreversible. So in physics, adiabatic processes are what you should be aspiring to. The computing process is not adiabatic. It's irreversible. So there's a whole branch of computer science on reversible computing. And Richard Feynman was quite a character when it came to that. One of the gates in reversible computing are named after. It's called the Feynman gate. And there are companies working on reversible computing now, because that could get us out of this debacle of having to use more and more energy, as you'll see in a minute as we go forward. So looking at the transistor density, and again, this is a log linear plot. We've had for quite some time, we've had an easy run. And this nomenclature here, 20N, it means 20 nanometers, but there's nothing 20 nanometers in it. It's just by the time we got to, I think it was about 28 nanometers, we then started to use a nomenclature which was in inverted commas, so nothing was. So if you see the A100, that's N7, and that's using what's called FinFET. So the gates were flat, and you had the source and the drain on a flat gate, and you had quite a lot of leakage. Then we made the gate a fin, and then we created a fin, and the gate went around the fin. The next technology, which is on the cards here, which is called gate all around, is where you use a nanowire and the gate goes around the wire. Every time we do these kind of big shifts, we reduce the leakage from the systems, and therefore should be able to get more energy efficient. But the trajectory, you can see it plateaus. It's slowing down a bit here as we go into the angstrom. The A is going from nano to angstrom, 10 to the minus 10 era of transistor compute. The H100 was at M5, and they could not get the B200, which is the latest NVIDIA accelerator for AI. They couldn't get it on the N3. So it's still FinFET technology. And obviously, if we can go more to the right, we can get more transistors per square millimeter on our die. Which is also useful as well. So break it down a little bit. I'm sorry, this slide is a little bit complicated, but breaking it down a little bit more. So the total power consumed by say, a microprocessor is made up of three parts. There's the static part, there's the dynamic part, which depends on the workload, what the processor is doing, and then there's the I/O part. You have to get data in and data out of the processor. And the static part depends on the number of transistors, the leakage current, which is a function of temperature. So the hotter we run these things, the more they leak. So, the push to run data centers hotter means you're going to draw more power, which is another interesting discussion. And the voltage at which the processor is operating at. The dynamic part depends on the capacitance of the gate, the voltage squared, and the frequency of the switching frequency of the gate. And there's also an activity factor. And I didn't, when I first did this calculation, I didn't put an activity factor in there when I did the calculation. And then I spoke to somebody who designs microprocessors, and they said, well, you always work with an activity factor around about 25%, which means that your transistor lights up every fourth cycle, the one that you're looking at. So only 25% of the transistors are active at any one time. And then there's the I/O part. Depends on you've got the NV link, so that's sending data to another GPU, and then there's the memory link. So in the A100, you've got 12.8 terabits per second throughput to the memory. You've got 2.4 terabits per second throughput to the MV link. Anyway, with all these numbers, you can work out the theoretical power here, 588 watts that A100 is. But when you buy one of those, you cannot get it to go more than 400 watts. Its thermal design power is 400 watts. So what's going on there? Why is there a shortfall of 188 watts? Well, there is another explanation for this. So if we actually put a factor in front of the P dynamic, which is the dynamic part, which is related to the workload, again, what actually happens is some of the silicon is dark. They call it dark silicon. So here, if you do this calculation, it says that only 34% of the transistors are engaged in the process at any one point in time. So you have an activity factor of 25% of them operational, and then you have 34% of them, this calculation, this is approximate. And then if you do that, then you get to 400 watts, which is the TDP for this processor. And the die size, you've got around 66 million transistors per square millimeter. The die size is 826 millimeters. This is the actual GPU here. And these are there's 5 of these operational, the 5 high bandwidth memory parts. And the interesting thing here is the actual flux, the heat flux at any one point in time in here could be 1.4 megawatts per square meter. If you go inside a nuclear power station, inside where the part where we're generating the heat, it's 1 megawatt per square meter. So now we have microprocessors in a data center that are air cooled, that have a higher heat flux than a nuclear power station. The sun, which is the highest heat flux thing that we know of, is only 10 megawatts per square meter. So so what is the limitation there? So the other thing is, and this is the temperature of operation. So when we acquire these microprocessors and we put them in our data center, we have to supply a temperature to a coolant temperature. And there's a fight between wanting to raise the temperature because it's good for your cooling system, but then there's an operational temperature that you need for your microprocessors. And one of the things that's driving it is here, these RAMs are stacked vias. They're 8 vias of silicon, 8 high. So the bottom one, the top one is seeing the cooling infrastructure, and you've got to get the cooling, you've got to cool the bottom one when you've got seven layers on top of that. So the restriction, there's a 20-degree jump between the top and the bottom here. And so the bottom one is limited to around about 90 degrees centigrade, which means that your top has got to be 70 degrees centigrade. So then we start talking about, well, we can't let the microprocessor go any hotter than 70 degrees centigrade. And by the time you talk about the losses, you need to supply cooling at a lower temperature than you thought you would, which is a challenge. So looking forward, say, to the B200, for example, which is the latest GPU that's on the market, a lot of things have changed. The memory I/O rate is higher. The NVLink, the communication is higher. If you look at the Chinese equivalent to what NVIDIA are doing, their racks are consuming 600 kilowatts per rack. And the majority of the energy in the Cloud Matrix 384, which is the equivalent to the NVIDIA's rack for AI, is actually in the interconnect, the GPU to GPU communication. There's a lot of energy expended in that. And that's why I don't know if you follow GTC and what NVIDIA does, where they have this conference every year in California where they announce their next processor. You're just installing billions of dollars worth of processors, and then there's a new one coming out. They were saying they're moving to silicon photonics. So this is linking together photonics with the silicon to try and reduce the energy consumption in the transmission. But overall, what we're trying to do, the Lambda idea is we're trying to get to this bullseye here. We're trying to increase the number of transistors, at the same time dropping the voltage where we don't have any error rates, because as you lower the voltage, the determinicity of the compute starts to reduce. And we're also trying to reduce the energy per switch. So we're aiming for that center part, which is challenging. So if you look at this one, when I did the calculations, the theoretical for the B200 is, and you can see that there's 2 GPUs and 8 memory modules, memory chiplets. It's 1,000 watts, its thermal design power, but theoretically it comes out to 1,722, which means that 26 or 74% of the transistors are dark. So dark silicon is an issue. If we could light up more of the transistors, we can only do that if we can get the power into the infrastructure. And of course, now we're looking at a much more dense 121 million transistors per square millimeter, and we're at 2 megawatts per square meter potential heat flux at any one point on the surface of that. So cooling this is quite challenging. So that's why you're seeing this now. So not a big box with massive heat exchangers and blowing lots of air. We are now in the age of liquid cooling. And I've worked in liquid cooling for over 15 years. 15 years ago, people told me, that's never going to work. Nobody's interested in that. Only high performance computing guys do that. And they do that behind a closed door. And they're not so bothered about the machine falling over. But now, we're bringing out these systems which are going into these racks. Now, this is interesting because this is 40 petaflops of training and 80 petaflops for inference. And in here, by the time you get this all racked up with everything, you're at 120 kilowatts in a rack. And that's 720 petaflops for training in one rack. And now, how do you power something like that? And how do you set it up in a data center? So here are some sort of reference diagrams from ASHRAE, which is the American Standard of Heating, Refrigeration, and Air Conditioning Engineers. They have a technical committee, 9.9, which looks at data center configuration for cooling. And what you can see here is that we have a liquid loop, which is, so you have a CDU, which is called a coolant distribution unit, which distributes now liquid to what you saw there, to these cold plates here. So you can see there's an inlet and an outlet, and inside here we pass liquid over some infrastructure which collects the heat into the liquid. And so if you wanted to say train GPT-4 on 28 days with 80 of these racks, the same amount as Lumi, you would be 10 megawatts. You'd be a similar amount of power as Lumi, but you're only 8 petaflops, 64-bit. So again, it's got more and more approximate compute. So we're moving away from traditional HPC. You cannot use these systems to do traditional HPC. So cooling it with liquid, and again, I'm sorry that this is a little bit, and I could see that the format hasn't come out so well here as it was on my laptop, but one thing to take away from here is that we usually put a heat spreader on top of the die, and we use thermal interface material, which is a connection to transfer the heat from the die into the heat spreader. And if you do some quick calculations here with thermal resistance, the thermal resistance across here to the ambient, if you want this case temperature to be 70 degrees, you would need your coolant to be 20 degrees. And for air, 20 degrees is too low, because we usually supply air in data centers at around 24 to 27. So here, this infrastructure, even with 1,000 square centimeters, spreading the heat over 1,000 square centimeters is challenging. So, so what do we do then? We look at using other, not air, as is the case here. We look at thermal resistances which are much lower, and you can see that we can use fluorochemicals, we can use oils, we can use water, or we can boil. Boiling heat transfer is a big subject in itself for cooling. And so here, this quick calculation here, if I just did it over 200 square centimeters in, say, a much smaller form factor with liquid, say here, if I used, say, water, which is a common, water mixed with glycol is a common way of direct-to-chip cooling, then you can see that this is easily cooled. This 1,000 watts from a B200 is easily cooled by liquid. And of course, it now means that we're in the era of liquid cooling. And now liquid cooling has two different types. The idea of this diagram is that we're moving away from moving air around here to now moving liquid into the IT with a combination of air, or in some systems, you don't use air at all. You completely cool the thing with totally with liquid. And so what this means is that we're now in the era of invading the IT with the cooling infrastructure. And in traditional data centers, you have the IT and the facility, and they're usually separated. Now, who's responsible now for the cooling inside the IT? That's the biggest, one of the biggest questions, yeah. And so there are a number of different ways of doing this cooling. You can do direct-to-chip. This is a general diagram from Google for their TPUs. Or here is a throw the servers in a transformer oil and throw radiators in with it and cool the whole infrastructure using this kind of thing. That was an experiment with some students that I ran a couple of years ago. And of course, when you do put the infrastructure together with direct-to-chip, like here with cool IT systems, you then got to connect all of these pipes together. And those pipes then have to be connected to your CDU, and your CDUs then have to be connected to your chilled water infrastructure. And that chilled water infrastructure has to be connected to a heat rejection system. So it gets quite a complex chain of heat transfer. I won't go into that. This is immersion cooling in action. So this is a project that we ran. I'm running out of time, Martin. This is a project that we ran a couple of years ago where we were immersing standard open compute inside a hydrocarbon. It's a very messy way to cool IT, but it actually does do a very good job. You have a lot of problems with because a lot of the IT equipment uses plasticizer in the cabling, and if you immerse plasticizer in a hydrocarbon, the plasticizer leaches. So you have to use non-plasticizer. So there's a lot of material compatibility issues that you need to consider. You also need to monitor the conductivity of the oil because it can change with time as well. But the other interesting thing about immersion cooling is that we ran the coolant at 30 degrees, and this is the consumption of the IT, 100%, say at 25 degrees. As we went up to 50 degrees, which as you ran hotter, and that's the P static. I said the current leakage is a function of temperature. You're seeing this is the only thing that's changing the energy consumption is the fact that the IT wants more power because it's leaking more energy. And so there's a 6%, 6.5% difference between running at 25 degrees and running at 55 degrees. So running hotter means you've got heat to use, but you're actually consuming more power in your electronics. So what do you want? Do you want higher grade heat, or do you want to use more power in your electronics? This is something that it needs to be discussed. So in terms of compute per unit resource, I think I will just say here is that operations per kilowatt hour or tokens per kilowatt hour is something that we're looking at now. There are some ISO standards on energy efficiency of servers. It's called ITEE. It's an ISO standard. The green grid looked at proxies on measuring how do you measure the energy efficiency of compute, because it's what you want. What you want is the compute, the digital services, but what you have to pay for is the kilowatt hour of electricity. So that's one way of trying to understand a metric that talks about energy efficiency. There is another metric that's used for the effectiveness of a data center, and you may have heard of this. It's called the power usage effectiveness, and it's basically the ratio of energy that goes into the whole data center divided by the energy that goes into the IT over 1 year, because seasons cause fluctuations in the cooling system, so you have to do it over 1 year. And you can see that from early 2000, we've dropped from 2.5 down to 1.6. We've plateaued at 1.6 average. This is Uptime Institute. The hyperscalers are always claiming 1.1, 1.2 for PUE because they can do things. They're on a much larger scale. They can do things at scale, and so they can make a better job of that. Water usage is another thing that is commonly talked about, and where we use water in the cooling system. So you use water. If you wet your thumb and you push it through the air, you can feel it has a cooling effect. It's the evaporative cooling effect, and that's used in data centers. And so water consumption is another thing that. And lastly, if we were talking about sustainability, and some of the things I'm interested in today, waste reduction, ICT longevity, can we use some of this? Can we give a second life to some of the IT? And we're looking at scenarios with data centers on how we can bring in second life of the IT. So going for, say, from a compute node to a storage node. So we could use mid-tier storage using older IT equipment. But we've got to weigh up the environmental impact of decommissioning that equipment to actually consuming the energy to run that equipment for another life. And that has to be factored in. And of course, I haven't talked about it much, but reuse of heat, there is another metric which is called energy reuse factor. And in Europe, the Energy Efficiency Directive for data centers is now pushing that new data centers should reuse the heat. It's being mandated now. And they don't do it only if it's technically or economically infeasible. But then you have to get some good guys in to show that it's not technically feasible. Otherwise, you have to do it. But on that note, I will finish, and this is a flyby of the facility where I work in the winter. And the winter temperatures can get down to -35 sometimes, which is actually quite dangerous to cool IT equipment with -35. So thank you for listening.
Thanks, John, for this very nice presentation. I have a question in the room. Some question?
No? We got one here. Yeah. It's quite good acoustics in here, isn't it? But it's
Thank you for the interesting talk. I understand it is out of scope for that, but I still ask the question.
Sure, yeah.
So,
yeah.
In your experience, do you do anything or significant stuff to actually optimize from the software application perspective energy consumption in the data center?
Yes, it's a topic that yeah. So one of the interesting things about data centers, I mean, is so in the IT side of things, you can slow things down. You can slow the clock speed as of the IT, for that's one thing. If you wanted to do that, obviously you will throttle the compute. But we have variable speed compressors, we have variable speed fans, we have variable speed pumps. And we've put together, we've run a data center as an experiment. It was an EU funded, where we've taken control of all the server fans at the same time as taking control of the fans in the cooling infrastructure. And we bring that into a control algorithm that balances the needs of the, because usually we oversupply, we overcool, and the system responds too slow when you're just basing it on temperature or pressure. And in that situation, we were just supplying enough air for the servers, and we kept the IT equipment at a constant temperature. So the workload causes the IT equipment to change temperature, but instead of the IT equipment changing temperature, we fixed the temperature of the IT, and we just changed the fan speed constantly up and down. Now, you would say that would wear out the fans a lot more, but it's actually easier to change a fan than it is to change anything else in a server. So they're expendable, and they've always got more than one, so they can compensate. If one fails, they've got another one that can overcome. So that's something we did do. And we always run at Ferrari speed in data centers. Everything is at high speed, which is why we consume so much energy. We can make it better by slowing things down and taking control of that. Does that answer the question a little bit? Okay, yeah, thank you.
Okay, thank you. We have just a quickly question. My comments are in the coffee break.
Okay, thanks, yeah.
Hi, thank you. It is no news to most of us here in the room, but of course there's a strong rebound effect, and you talked about the increase in energy efficiency of the hardware several times, but we will probably always develop new applications that will consume that increased compute, or we will just use it more. So do you have any ideas on how to act against this dynamics?
That's for the social scientists to sort out. I think it's you're right. Yeah, we make it more efficient. Javon's paradox is known as well. If you make something more efficient, don't be surprised the consumption goes up. And there's so many examples of that. And the computer industry is one example of that. And you're right, we're going to find more and more uses. And you've got Sam Altman who's saying, we need more power to run these data centers. Is this crazy? Where is the limit? We're trying to make it more efficient, but it's still a long way to go. On that aspect, I think it's data centers don't consume energy. It's the applications that consume the energy, if you like, but the applications don't consume the energy. It's the users that are using those applications that consume the energy. So you need to go to the source of the problem, which is the user. And I don't know how you change that. I don't know, if you had on your phone that you were interacting with an application where the carbon intensity at the moment is higher, and if you had a forecast that the carbon intensity in 2 hours' time will be half of what it is now, would you stop what you're doing and then go back to the application 2 hours later? That's a question to you. Would you change your habits based on the fact that you're given information that you are now using a resource which is high? How many people look at buying an airline ticket based on the carbon intensity of the flight? You usually go by price, you don't go by carbon intensity. So these are the things that we need to address in this industry, yeah. You either do it by hurting the pocket is one way, or legislation, or you do something. I don't know. It's a challenge.
Okay, thank you, John. We don't have a time for question now. Maybe in the coffee break.
I'll be around, so if anybody wants to challenge me on it.
Available for.
Yeah, I'm available for
Okay, thank
to
you,
be challenged.
John.
Thanks a lot. Yeah.